For 10.3, we're going to look at logarithmic functions. We're going to graph them and write a function in both exponential and logarithmic forms. So a logarithmic function is just the inverse of an exponential function. And the log of a number, or the logarithm, log, of a number is the exponent needed for the base value to equal that number. Let me tell you what I mean here. So for an exponential function, y to the b, or y equals b to the x, this is what we've been working on for the last couple sections of notes. Now we can rewrite that using a logarithmic function as the inverse of it. And I want you to look at the components here. So we have b, our base. That's going to be the small number here on the log. The exponent, x, is kind of like the answer over here after the equal sign. And then our y, our function name, is going to be the main number of the log function. Okay, so let's practice flipping these things around. But in general, you can start with the base and go b to the x equals y, kind of in this circular rotation here. So we're going to rewrite these exponential functions in logarithmic form. So we have 2 to the third power equals 8. So this is going to be a log with base 2. That's the base of the power. Log base 2 of 8 equals 3. So you see how the numbers just kind of get rearranged. But in general, after you're done, you've got to think 2 to the third power equals 8. Like that. Okay, 3 to the fourth equals 81. This is going to be log base 3 of 81 equals 4. Now these parentheses, you'll often see these written without them, as you can see down here. But I like to write them just so it's clear what's contained inside the log function when I'm writing these by hand. Okay, 5 to the x equals 25. This is going to be log base 5. So the base is always the same as the exponential base. Kind of think of that as the base number. Of 25 equals x. We'll actually get to solving some of these later, but for now we're just rewriting them. And example D, we have log base x of 64 equals 3. Okay, so the log function equals the exponent needed for the base number to equal the number inside the log. Okay, now let's practice rewriting the logarithmic functions into exponential form. Just kind of going backwards here. So log base 2 of 32 equals 5 tells us that 2 to the 5th power equals 32. Now you can know if you get these wrong because the power won't be equal. If there's an exponent, you won't know. Or I mean, if there's a variable, you won't know exactly. But for these number ones, you can know if it's true or false, if you wrote it correctly or not. Example B, log base 5 of 125 equals 3. So that's 5 to the third equals 125. Example C, log base 3 of 9 equals x, so that's 3 to the x equals 9. And finally, log base x of 16 equals 4 gives us x to the 4th equals 16. So remember, we're going around the log like this. Now let's solve some of these, find the value of x. So we're just going to rewrite these as exponential functions, and then we can more easily kind of intuit what the answer should be. So log base x of 729 equals 6. That's going to be x to the 6th equals 729. Now remember, if you need to find an nth root of a number, so I need to find the 6th root of 729 here. So I'm going to go 729 y root 6, that'll give me 3. So x equals 3 for this one. 3 to the 6th power equals 729. Example B, we have 3 to the 3rd power equals x. So 3 to the 3rd, that's 3 times 3 times 3. That's going to be 27. Example C, x squared equals 49. Take the square root of that. I know x equals 7. And example D, we have 6 to the 4th equals x. So I can do 6 to the 4th power. I get 1,296. So if there's an x in your log function, just my suggestion is to rewrite that as an exponential function, and then you can solve for x. Okay, so let's graph a logarithmic function here. Now, recall what we said above. This is an inverse function of an exponential function. So we might have to adjust our process a little bit here. We're going to make a t-chart. Make a t-chart here, x, y. But it can be helpful to rewrite our function as an exponential function because mentally that just makes more sense. It's hard to know what the process is for a log function, but if I rewrite it as an exponential function, this can be easier to get our point. So let's rewrite this. We have log base 2 of x equals y. So 2 to the y power equals x. Well, this is a little strange. Normally, x is our input, and we get the answers out for y. But in this case, y is going to be our input because that's what's going to affect our function, and x is our output, which kind of makes sense if you think about it because we are dealing with an inverse function, and those switch x and y. So now we're going to use y as our input. So let's put in some numbers here for y. -1, 0, and 1. We'll start with these. Now let's see what happens. For -1, if I put -1 in for y, I get 2 to the -1 power. Well, that's 1/2. So I have a point at 1/2 -1. That's right here. Okay, let's put in 0 for y. 2 to the 0 is 1. So I have a point at 1, 0. And let's put in 1 for y. 2 to the 1, power of 1 is 2. So I have a point at 2, 1. Starting to see this picture come together, but I want to do a few more points. Maybe I should have made a larger chart, but let's do -2 and 2. See where that gets us. Okay, if I put -2 in for y, that's 2 to the -2 power. It's 1 over 2 squared, right? We switch it. We flip the fraction. So 2 to the -2, let me use a different color here. 2 to the -2 is 1 over 2 squared, which is 1/4. So I get 1/4 for -2. Okay, this is kind of making sense now. If you remember what an exponential function looks like, right? It's sort of this curve that approaches 0 but doesn't touch it. And this is the same thing, but it's been reflected over this line. So it's kind of a similar graph looking to the exponential function, but it's mirrored across the coordinate plane. Let's put in 2. 2 squared is 4. I have a point at 2, 3, 4, 2. So here's my picture. Here's my graph like this. And which should make sense because if I take the actual inverse of this, just for fun, that would be 2 to the x equals y. And we've graphed that before. 2 to the x looks like this, right? This is the inverse function of that. And that should match. So this is y equals log base 2 of x, which is the inverse function for y equals 2 to the x. And if you look at that graph now, that is reflected across that line y equals x. So truly this is the inverse of that function. So whenever you graph your log functions, you're going to have to use your y values as the inputs because they are inverses of an exponential function. So something to watch out for. Now that we know the shape, this can be a little easier. So let's practice a couple of these. Let's graph these log functions. And again, I'm going to rewrite these as exponential functions, not the inverse. I'm just going to rewrite this one as an exponential. So this would be 3 to the y equals x. And now we'll make a t-chart. And really, now that we know the shape, we can really just use -1, 0, and 1 for our y values. But you could do -2 and 2 if you want to get a complete picture. It just probably won't fit on the graph. So -1 put in for y, we get 1/3, which is about right here. 0, 3 to the 0 is 1. We got to point at 1, 0. And if I put in 1 for y, I get 3. So 3, 1. And we can see this graph is going to get closer and closer to x equals 0 and keep going this way. So we have a new asymptote for the log functions. It's the y-axis instead of the x-axis. Okay, let's graph one more. So again, changing it to exponential. Remember, f of x you can just think of as the y. So we have 1/4 to the y power equals x. Let's make a t-chart. Put in those numbers for y this time as our input. So -1, that flips it, gives me 4. I have a point at 4, -1. 0 gives us 1, as always, 1, 0. And 1 for y gives us 1/4. So now our graph is going this way. So with a fraction base, I'm going up, but the asymptote is still the same. Still x equals 0 here, but my direction is sort of flip-flopped. This one is a little harder to imagine as the inverse of an exponential decay function, but that would have looked something like this, which is reflected across that middle line. So a little harder to visualize compared to something like example A, which was pretty straightforward. If we drew that reflection line, that makes a little bit more sense because it doesn't cross it. This one crosses that reflection line, so it looks a little something like that. But either way, not really necessary to consider those inverse functions as you graph these. Just remember you have to use your y value as the input when you make your chart. Kind of flip-flops that. So there's graphing at logarithmic functions. A little difficult potentially to wrap your head around, but once you get the idea, rewrite it as an exponential function and then use your y values as the inputs instead of x.